equals mc², when light found its weight. Presented by augmented Newtonian dynamics. By the late 19th century, light was considered immaterial. It illuminated the world but seemed to have no weight. Physicists assumed it was a wave, energy without mass. That view began to change with James Clerk Maxwell. His electromagnetic theory unified electricity and magnetism into a single field. Maxwell's equations showed that oscillating electric and magnetic fields can sustain one another and travel through space as a self-propagating wave at a fixed speed, the speed of light. From this, Maxwell concluded that light is an electromagnetic wave. But more importantly, he realized that such a wave must carry energy and also momentum. By analyzing the energy stored in the electric and magnetic fields, what later became known as the energy density equation, Maxwell demonstrated that electromagnetic radiation possesses energy distributed throughout space. Any system that can transfer energy can also exert force. Therefore, light must be able to apply pressure when it strikes a surface. To describe this transfer, he introduced what later came to be called the Poynting vector, representing the rate of energy flow through a unit area. From this, he derived the expression for radiation pressure, showing that electromagnetic waves exert a measurable push proportional to their energy flux divided by the speed of light. In modern terms, this is expressed by the momentum density equation, which states that wherever light carries energy, it also carries momentum proportional to that energy divided by the speed of light. This conclusion, reached in 1873, 27 years before Planck's quantum hypothesis, was one of the most remarkable predictions in physics. Long before the photon or the idea of quantized light, Maxwell had already revealed that electromagnetic waves behave dynamically, carrying both energy and momentum as though they possessed inertia. From Maxwell's conjecture to experimental proof. Maxwell's conjectures on light's energy and momentum led to intense discussion and growing interest among physicists in the last quarter of the 19th century. His claim that light waves could carry both energy and momentum challenged deeply held assumptions about the separation between matter and radiation. If light could transfer energy and exert pressure, then in some sense it behaved as if it possessed mass. This was a striking and uncomfortable idea. To most physicists of the time, light was the very symbol of the immaterial, a continuous oscillation in an invisible ether, not a substance that could apply force. In 1876, Adolfo Bartoli, an Italian physicist, approached the question from thermodynamics. He reasoned that if radiation carried energy but lacked momentum, one could, in principle, construct a device that converted heat from a single source into work without any loss, a perpetual motion machine of the second kind. Such a machine would violate the second law of thermodynamics. To preserve that law, light had to exert pressure. Its energy flow had to be accompanied by momentum. Bartoli's argument was theoretical, but persuasive. It implied that light behaves like a material stream, capable of pushing objects that absorb or reflect it. The next challenge was to measure this effect. Around the turn of the century, Pyotr Lebedev in Moscow succeeded in detecting this pressure experimentally. Using a torsion balance of extreme sensitivity, he demonstrated that light shining on a small reflective surface caused a measurable deflection. Almost simultaneously, at Cornell University, Ernest Nichols and Gordon Hull performed a similar experiment with even greater precision. Their independent results agreed: electromagnetic radiation exerts a real, mechanical pressure on matter. These measurements, published between 1899 and 1903, confirmed Maxwell's prediction beyond doubt. Light, though massless in the ordinary sense, could behave dynamically as though it carried momentum, and therefore inertia. This realization created a major conceptual shift. If light, the archetype of something without mass, could push matter, perhaps energy itself had the properties once reserved for mass. The boundary between the material and the immaterial was beginning to blur. Poincare and the Curies. Linking theory and proof. In 1900, Henri Poincare addressed one of the puzzles left by Maxwell's theory. When a body emits light, the radiation carries momentum. According to Newton's third law of motion, every action must have an equal and opposite reaction. To preserve this balance, Poincare proposed that electromagnetic radiation behaves as if it were a fictitious fluid with an effective mass equal to its energy divided by the square of the speed of light. He showed mathematically that radiation carries momentum and that a radiating body must recoil slightly upon emission, just as a cannon recoils when firing a projectile. Although Poincare did not extend this equivalence to all forms of energy, he had made the crucial connection: energy has inertia. The idea that energy and mass are proportionally linked was clearly stated in his 1900 paper, 5 years before Einstein's analysis. At almost the same time, a very different kind of discovery was unfolding in a Paris laboratory. Marie and Pierre Curie were studying the spontaneous emissions from newly discovered radioactive elements such as radium and polonium. Their measurements revealed that these substances emitted enormous amounts of energy in the form of penetrating radiation, while their total mass decreased measurably over time. No chemical process could account for this loss. The implication was clear: a small quantity of matter was transforming directly into energy. The Curies had uncovered, through careful experiment, what Poincare had predicted in theory. They did not express it in the form, but their data demonstrated that energy release is accompanied by a proportional decrease in mass. This was the first direct evidence that the boundary between matter and energy is not absolute. Matter could change its form, giving up part of its substance as radiation. Later, Einstein would supply the mathematical framework explaining why the proportionality factor between the two quantities is precisely balanced. But the experimental foundation, that matter and energy are interconvertible, was already visible in the Curie's work years earlier. Albert Einstein and E=mc². In 1905, Albert Einstein published 2 separate papers. The first, on the electrodynamics of moving bodies, established the theory of special relativity, a framework showing that the laws of physics and the speed of light are the same in all inertial reference frames. This was a purely kinematic treatment of space and time. Later that year, in a brief follow-up note, "Does the inertia of a body depend upon its energy content?" Einstein drew a quantitative link between mass and energy. He reasoned that if a body emits energy as radiation, it must lose mass. The famous relation E=mc² appeared here for the first time. Einstein later summarized the result by saying, "It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing." Although E=mc² was derived separately, it fit naturally within the structure of special relativity. The full relativistic expression for energy reduces to E=mc² when the body is at rest. The principle unified mechanics and electromagnetism. Mass became a form of stored energy. Energy carried inertial properties. Light provided the bridge between the two. As radiation, it demonstrated that energy could behave as if it had mass. As emission or absorption, it revealed how matter could convert part of its mass into radiant energy. The earlier experiments of Maxwell, Bartoli, Lebedev, Poincare, and the Curies had already shown pieces of this relationship. Einstein's work combined them into a coherent theory. After 1905, the consequences became increasingly clear. In nuclear reactions, tiny reductions in mass produce vast amounts of energy according to E=mc². In high-energy physics, photons can produce matter-antimatter pairs. In astronomy, stellar energy output arises from the same relation. Hydrogen nuclei fuse to form helium, releasing the mass difference as light. The equation therefore describes a universal conservation rule. Whenever energy is released, an equivalent quantity of mass disappears. Whenever energy is absorbed, mass increases by the same amount. E=mc² does not depend on relativity alone. It can be derived from conservation of energy and momentum, but relativity provides the framework in which it is most naturally expressed. It defines how energy, momentum, and mass transform between observers moving at different velocities. Light remains central to this framework. Its constant speed, c, links space and time geometrically, and also converts between energy and mass numerically. It is both a standard of measurement and the medium through which mass and energy reveal their connection. By uniting these concepts, physics replaced the old division between substance and radiation with a single continuum. Matter is energy confined, radiation is energy released. The two obey the same laws and differ only in form. From Maxwell's first prediction of light pressure to Poincare's fictitious fluid, from Curie's measurements to Einstein's synthesis, the understanding of light's momentum transformed modern physics. What began as a paradox, that something weightless could push, became the cornerstone of 20th century science. Energy has mass, and light is the proof. Special relativity, the equation and the theory. There is a curious belief, deeply rooted in modern physics, that because E equals mc² is true, special relativity must be true as well. It is a comforting assumption, elegant, circular, and misleading. The equation E equals mc² is not born from the geometry of spacetime but from the arithmetic of conservation. It tells us that whenever a system releases or absorbs energy, its inertia adjusts by a precise and measurable amount. In this sense, it is a statement of energetic accounting, not of relativistic motion. Decades before Einstein's formulation of relativity, James Clerk Maxwell had already shown that light carries both energy and momentum, and Henri Poincare, in 1900, had described the electromagnetic field as a fluid possessing an effective mass. These were deductions of balance, not of geometry. They did not require time dilation or length contraction, only the symmetry of energy and momentum in emission and recoil. When Einstein wrote E equals mc², he was not proving relativity, he was proving consistency. The two principles, relativity and mass-energy equivalence, share a harmony, but not a dependency. Relativity gives E equals mc² a natural home, but the equation itself stands perfectly well without it. To say that because the equation holds, relativity must hold, is like saying that because a wheel turns, the entire road must curve. Both describe motion, but one does not prove the geometry of the other. In truth, E equals mc² speaks of what changes when energy moves, not how it moves. It governs transformation, not transformation's law. Its truth is empirical, local, and immediate, as true in the radioactive glow of Curie's lab as in the furnaces of the stars. Relativity, on the other hand, is a framework of perspective, a way of reconciling measurements across motion. The two share a language, but not a birth. Conclusion: light, matter, and the question of the medium. Einstein often referred to light as the link between energy and matter, a phenomenon that seemed to defy classification as either substance or motion. He regarded its constancy as the key to the structure of the universe, the one natural quantity that connected space, time, and energy into a single order. In this sense, he considered light to be the mediating factor between energy and matter, the agent that allows one to transform into the other. It was, in his eyes, the operational principle of nature itself, a kind of universal instrument through which the laws of motion, mass, and energy achieve their balance. Yet this view was built on the assumption that light required no medium of propagation. If, however, a genuine physical medium were ever demonstrated, an ether in the modern sense, the interpretation of relativity would necessarily change. The propagation of light would then have a definite physical basis, and the effects of time dilation and length contraction would no longer be fundamental geometric consequences but secondary phenomena arising from motion through that medium. Electric and magnetic fields would cease to appear as abstract, independent entities and instead be understood as local expressions of an all-pervading continuum that mediates every interaction among light, energy, and matter. This is precisely what augmented Newtonian dynamics proposes, that space itself is filled with a sea of virtual photons, a physical substrate through which radiation propagates, matter interacts, and gravity emerges. In such a framework, Einstein's equation E equals mc² remains valid as a statement of local energy equilibrium, but its meaning is extended and clarified. It no longer describes a purely geometric relationship within spacetime, but a dynamic process occurring in a real, continuous medium, the universal field that links light, energy, and matter in every physical interaction. The evidence for the existence of such a medium, namely dark matter, is overwhelming. Vera Rubin and later astrophysicists have estimated the amount of dark matter in the universe as comprising between 85% and 90% of the universe. The physical properties of dark matter also exactly match the properties of a light-supporting medium. Let us wait and see, sooner or later we will know.